So hello everyone. In this video we will be using the taste virtual machine to create binaries and bit files for the Brave Large Nano Explorer FPGA board. You can obtain the taste virtual machine by using your browser and going into taste.tools, then go into installation, and you can see here that you can download the Debian Buster based Taste 10 virtual machine. It's an OVA file, which means a virtual appliance, and then you launch VirtualBox, you import this particular virtual appliance, and you launch it, and you end up in exactly the same state you see here, with the default terminal coming up and giving you some information. Information you should be aware of is that we are user taste, as you can see here, and our password is tastevm. And as it is indicated here, to update to the latest version, we need to execute these commands. So we need to go to the tool.src folder and launch update taste. I have already done this, and so my virtual machine is up to date, meaning it includes the work we did over the last few months to support the building of applications and the synthesis of FPGA bit files for the Brave Large. So I can now create an application by launching the Taste IDE, the Taste Space Creator. I just went into an empty folder and launched Taste, and since we will be targeting the Brave Large, let's call this Large Bravery. So the Taste Integrated Development Environment is starting now, the Space Creator as it is called. We already have a default project file generated automatically with all the necessary baseline information. And by default, we are in the interface view editing, where we are defining the interfaces that our design is using, and the functional blocks hosting these interfaces. So as the helper message says here, we right-click to add a function, and then we use control-click to connect functions together. So I'll delete the help, and as it says, I will right-click and create a functional block, the first functional block, function 1. And I'll create another one, function 2. So functional blocks in Taste, you can think of them as groups of interfaces, which at a subsequent stage you deploy into specific executable platform targets. So in a distributed system, for example, I could host this one on, let's say, a Linux machine, and this one on a Xeon processor or an ARM processor. And when the interfaces between them communicate, Taste will create automatically all the communication machinery to make it happen. But of course, in the Brave Large, in this proof of concept implementation we have, we will host both of them inside the Cortex-R5 of the Brave Large. And what will we implement here? We will have, first of all, in function 1, we will create a new provided interface. This is a nomenclature we use in Taste. Provided interface means that this functional block provides the code and the logic for this interface, whereas a required interface is something it requires to function. So the first interface we will have here is a cyclic. It will execute by default, as you see here, once every second. Let's call this pulse. And you can see that there are a number of other parameters here. For example, you see that we will have a stack size by default of 1K. And now this interface will be called automatically once per second in the binary that Taste will create for the R5. And we want it, every time it activates, to call into an interface that is provided by the second guy, by the functional block 2. So this interface will be adding 2 numbers. And there's a number of choices in addition to the cyclic one. A crash course on them is that the sporadic interfaces are asynchronous interfaces. They're fire and forget. So the caller doesn't block. He just send something and it will be computed wherever it is computed. Whereas the protected and unprotected ones are synchronous ones. So they have blocking calling conventions. And the difference between protected and unprotected, as the name suggests, is that the protected ones have mutual exclusion machinery protecting potentially shared state, global state inside the particular functional block. In our case, we have no such need, so we'll just use unprotected, the simplest possible one. And of course, since we want to add two numbers, we need to have input parameters. So I'll just use two of them, P1 and P2. You can see that both of them are in direction in, so they're input parameters, and we will be creating an output parameter. Now, obviously, whenever we're talking about parameters of interfaces, there's the necessary concept of what type are my parameters. And in the case of taste, where we can have distributed systems as well, what is our encoding protocol? So you can imagine that if these guys are living in different architectures with different, for example, endianness or integer sizes, we would have an issue if we just used, let's say, the C calling conventions and we said that this is an int or an unsigned or a long or whatever. So taste uses ASN1 to describe the types, as we will see soon. And in our ASN1 grammar, our default ASN1 grammar, we have a myInteger type, which is chosen by default, and is the one we use. And we also say, because both of these functional blocks will live inside the Cortex-R5, so there's no need to compress the information or encode it per ASN1 with the unaligned packed encoding rules or the advanced control notation. We just use native encoding, which means we just transfer them as is. And that allows us basically to communicate with minimal fuss, minimal overhead between the two functional blocks. Now, the only thing that is left from an architectural viewpoint is that I will control click as the thing suggested, and now, as the message at the beginning suggested, and now you can see that we have a required interface on function 1 that says, for me to function, I need to be able to call this guy. And taste will do whatever is necessary when we call this add to numbers to communicate with the other functional block wherever it may live. Initially, we will live in the R5. At the next stage, you will see that we will move this to the FPGA. So from an architectural standpoint, in terms of interfaces, this is it. This is our design. I can file, save all. And now I can move into the second stage, which is, okay, we have these guys, but where are they going to be deployed? So I will right-click here and add a new deployment view. And when you do this, Taste allows you to select what is your deployment target platform. And you can see that in addition to the rest, we now have the Brave Large deployment target. So I will put it here. Taste by default targets things that can potentially have time and space partitioning machinery. Think of hypervisors, for example. And of course, in our target, which is just FreeRTOS, there is no concept of partition, but still the nomenclature in Taste creates partitions inside the deployment targets. So we can now bind our functional blocks, in our case function 1 and function 2, inside the partition 1, which basically means the ELF binary that we will create for our Brave Large Cortex-R5 processor. And that also concludes our deployment information that we need to choose where, how the design will run, in what kind of target it will run. Now, going back to the interface view, something we have not specified is that, okay, this is our breakdown in terms of interfaces, but what is the implementation language? If I go here in implementations, you see that by default we use SDL, which is a language very nicely designed for state machines. But for this simple example, I'll revert this to C. I will go down to the lowest common denominator of the universe, which is the C language, for both functional blocks. And now that I have my design in terms of interfaces, functional blocks, and deployment done, I can actually go down into the nitty-gritty and provide the implementations of these interfaces. So I can go here and edit implementation. When I do this, Taste launches the necessary code generators to create the templates for my code. Something I neglected to mention, if I go back to the interface view, is that I said before that the types of my parameters are specified in ASN1, this myInteger thing. Let me just show you this. So if I open the ASN1 grammar, you see that what myInteger actually stands for is an integer that goes from 0 to 10,000. And I should remind you that I said before that the implementation language is C, and perhaps you were thinking, okay, then can't I I just use unsigned or int or whatever. Yes, but taste follows the model-based software engineering methodology, which means that regardless of whether I run in a Cortex-R5 or whether I create a distributed system where function 1 lives in Linux and function 2 lives in the R5 or in a Leon Spark or whatever, I want to be able to communicate regardless of what the endianness or the integer sizes are. And this is why we specify things in an abstract manner, and then we have compilers that translate this into the corresponding implementation language that we have chosen for our functional block, in our case, C. So because we chose C for our implementation language, you see that what taste generated for my function 1 is two things. We have the startup function that is called whenever my system begins. We have the pulse function that will be called once per second. And because we specify that we have a required interface that the pulse will be calling out to add two numbers, taste also created a prototype that specifies, following the ASN1 conventions for the types chosen in those particular interfaces. It says that, if you remember, we had two inputs and one output. So indeed, taste created a constant pointer to an ASN1 semi-integer as the first parameter. Another one for the, not constant pointer, sorry, pointer to a constant value, because it's an input, so we're not supposed to modify it for the second one as well. And a non-constant pointer to the output where we will write the result. So I will take this prototype, because I will actually be needing it, and inside the pulse function, which will be called once a second, I will call this remote guy, the remote interface, my required interface, and I need to pass here, of course, pointers to the arguments. So I will remove these guys, and I will declare local parameters, P1, P2, and P3, which I will be passing here. So I will be passing pointer to P1, pointer to P2, and pointer to P3. And my remote functionality will add P1 and P2 and will store the result in P3. Of course, the thing is that I want the repeated invocation of PI pulse to exhibit some behavior. I want to see something output. So I want these values to actually be maintained across invocations. So by using the static prefix here, I turn these variables into more or less global variables. I move them into the BSS section, which means that they are zero initialized, and also that across invocations, P1 and P2 will hold their values. So every time I call them, I can actually increase P1, and I can increase P2 by 2, say, so that every time I call them, I will see a different result. Speaking of seeing results, of course, the issue here is that I'm deploying on the Brave Large. So I have a UART, I have a serial output, which I want to dump some information out. And in the port we did for the Brave Large, we also ported a small implementation of the printf function, because remember, we don't have a libc here. We have a small embedded environment. So we have implemented a printf function, which will tell us that inside function P1 PI pulse, we added %u and %u, and we got back a %u. And we'll have a new line afterwards. And I will cast, I will cast my parameters P1 and P2 to unsigned, because that's what I'm using, %u, so that I can see what exactly happened when I called my implementation. We'll also do the same for this guy. So debug printf to see that we actually do have indeed a startup call when the system begins, where I can do global initializations for my functional blocks, whatever initialization logic I need. In our case, we don't need much. And that concludes basically the implementation of the function 1 functional block. So going back to our interface view, we provided implementation for my pulse interface. Let's do the same now for the implementation of the functional 2 functional block. which is actually much easier since we already know that we just need to add two things. So I will just say that the out pointer should get the inputs added, and that's pretty much it. And you can see here that the first two parameters, because they were input parameters, are annotated as const, so these are pointers to constant integers. So even if I try to do here a modification, the compiler would stop me. You can't modify the constant parameters. And that's it. The implementation and the design is complete. And that means that if I did my job correctly and I don't have any typos, which I hope is the case, I can now go to my deployment view and I can click on the hammer here to ask for a build. Yes. And see that we are building. You see that taste calls the ASM1 compiler. It translates the design that I did into the corresponding lower level, let's say, semantics. It compiles the FreeRTOS code that we did, and it creates a binary. And you can see that not only did it create a binary, it actually also reported that our pulse function is using 336 bytes out of the 1K we allocated for its stack. So we will automatically detect stack overflows if we had something at our compile time. If we had a stack overflow, we would be able to detect it. Let's go back to the terminal where we launched the IDE to see what we have done here. So we have the large bravery folder where we did all this design. Everything that we did, which is important here to understand, is not in some cryptic binary representation or whatever. It's stored in ASCII files, standards compliant ASCII files, using the proper languages to describe things. So the types, for example, which I said are in ASN1.1, you can see are in the ASN1 file. And you can see that even though we used my integer in ASN1, you can actually also have booleans or enumerated things or structures of things, what other languages call struct or records with multiple things, or arrays, an array of two enums and so on and so forth. This is relating to the types necessary in my design. And the corresponding interface design is in my AADL, so the architectural description language, which is another standard. So you can see here that what we described about the add two numbers is formally translated by taste into the corresponding AADL file. So everything you see on the graphical user interface has a corresponding, a one-to-one correspondence with a formal, strict language parsed by machines, whether it's ASN1 or AADL or whatever. And this is what allows taste to build everything in the end and create the necessary glue to make them work. Now, under the work folder, since we built, you can see that we have now, binaries, a file which is an ELF, so an executable ELF targeting ARM architectures. And it is indeed a file that was compiled to execute the logic we described. Now, assuming I haven't messed up, the generated binary can now be run on the board. So I will copy it from the virtual machine where I built the binary into the machine where in the lab where I have set up the board, where I have set up the Brave large board. And to prove that I'm not making things up, I will MD5 sum the work binaries partition 1, and inside the board, inside the machine that hosts the board, I will do exactly the same MD5 sum. You can see that this is indeed the binary we just built, copied across. Now, in here, I have set up all the necessary tools to run the binary on the board. And I have, on the top left window, I have the NanoExplore command line utility that loads the bit stream that initializes the R5. Then here I have the OpenOCD that offers a GDB server that allows me to communicate with the R5. And on the top window, top right window, I have Minicom dumping the serial port, the UART, with the output of the R5. And here I will launch GDB on the binary. First I will connect, of course, to the GDB server. Monitor reset halt. And oops, what did I do? Monitor reset halt. And I will load the partition 1. And when I run it, we can see on the top right window that indeed the logic we provided in the implementation of our interfaces in our functional blocks indeed works the way we expect it to work, and we perform the necessary additions. So now that we've seen the application work on the board, one thing I also wanted to demonstrate is what taste created behind the scenes. So if I create, first of all, some navigation tags to allow my editor to jump between symbols, and I open the main entry point, which is inside app.c, that is generated, we can see that after initializing Brave itself and the CL port, taste calls the initialization functions for my the two startup functions for my two functional blocks. So you can see that if I trace init function 1, I will end up calling function 1 startup, which is indeed what we wrote inside our IDE as the desired logic for the startup, which is why we see the message startup when we did the test. And after it has called the startup functions, we will create a thread for our cyclic, and that is necessary because our cyclic is supposed to execute once every 1,000 milliseconds, and we do this by spawning a task, a FreeRTOS task, which is appropriately timing itself to call into our pulse logic once every 1,000 milliseconds. You can also see that here that in the code that is created, we are using the static versions of the FreeRTOS tasking primitives, which allow us to be to reserve the space for whatever we need up front. We don't depend on dynamic memory allocation, because this is something that we don't like in safety critical embedded code. So this is why we use the xtask create static and not the xtask create family, or let's say, of functions. And you can see also the 1024 bytes that we reserved for our stack. And after that, we start the FreeRTOS scheduler, which will appropriately call our tasks, in this case, the task invoking our cyclic. If you're wondering, okay, where's the task for the function 2? Remember that function 2 was an unprotected interface. That means that it has blocking calling semantics from whoever calls it. So it doesn't need a thread of its own. It will be called within the context of the thread that runs the function 1 pulse. And that concludes this first video with the two functional blocks residing in the R5. In the second video, we will move to see the function 2 logic automatically translated by taste into its VHDL form, being synthesized and run on the fabric, on the FPGA of the Brave Large. See you there.